X27 entropy. Find the fourth statement regarding the ideal gas equation PV equals NKVT. If a thermal system is not in thermal equilibrium, then we cannot make use of this equation, evidently. It is not applicable in the middle of a free expansion. In a free expansion, P and V are not defined, so we cannot make use of the equation. In an isothermal process that keeps the temperature the same, the macroscopic variables are correlated. Hence, once the temperature, both temperature and pressure, no, temperature and volume are fixed, then pressure is determined, as long as N is fixed. In an isobaric process that keeps the pressure the same, temperature, volume determined, T is fixed. Once V is known, temperature is fixed. Once temperature is fixed, then volume is known. Yes, only 3 of them are independent. Saying the same statement. You can see expansion. It's a free expansion and free compression. Free expansion happens virtually always. It is improbable to keep the volume the same and keeping the vacuum invariant. As time goes by, in thermal, a system should reach the thermal equilibrium state that is a kind of free expansion. However, the reverse process doesn't happen at all. It is virtually impossible. So we have to distinguish the two kinds of processes. One is reversible, the other is irreversible. Irreversible is impossible to reverse. Once the stomach digests the food, you cannot return the food. The irreversible process. Mirror gets dirty, you need to clean it up. So cleaning up does not happen spontaneously. So getting dirty is irreversible process. If the reverse process of a given process does occur spontaneously, it happens. The backward process happens. It is called reversible. Ice in boiling water melts, but it is very difficult to believe that in a boiling water, ice grows up. So it is irreversible process. If a process develops toward the state having a significantly greater probability, then the reverse process has the probability that is significantly smaller. Therefore, it is irreversible. The plot shows the free expansion, except that the last stage, which is in thermal equilibrium, during the whole process of expansion, it is not in thermal equilibrium. We cannot make use of the equation the ideal gas equation is not applicable in that case. Both volume and pressure are not defined during the whole procedure. Temperature is well defined, however, except for the initial and the final states, it is not applicable, right? Average kinetic energy is invariant, so temperature is well defined throughout the process. It is a reverse process, the reverse process of free expansion. So it is called the free compression. Free compression doesn't happen at all, but probability of happening this process is not actually zero, although it is a vanishingly small. While free expansion occurs spontaneously, it happens spontaneously. Free compression does not occur spontaneously, right? Probability of this process is essentially zero. Yes, it is virtually zero, almost zero, and there is nothing wrong to say that the probability is approximately zero, although this probability is not exactly zero. But because this process won't happen spontaneously, it is irreversible. What is irreversible? This is a reverse process of a free expansion. Therefore, the free expansion is irreversible. Free expansion does happen. Free compression does not happen spontaneously. Therefore, the free expansion is irreversible. Find a false statement regarding the free expansion from a state to another, where n is an integer, the volume expands. The free expansion. During the free expansion, there is no heat transfer. Sure, it is delta Q is always assumed to be zero. During the free expansion, it does not work at all. Therefore, the temperature is the same throughout the process. During the free expansion, yes, temperature is the same. Before the expansion, it was in equilibrium. We can say after the expansion, we can still make use of the equation, ideal gas equation, but replacing the indices. Only the number of molecules are invariant. However, the temperatures are the same. Temperatures are the same. Pressure and volume changes. Because the temperature is the same, the product of pressure and volume should be the same. Volume has been increased, therefore the pressure has been decreased. Now we consider the reproduction of an irreversible process with a corresponding reversible process. We focused on the fact that the temperature is invariant in a free expansion. Now we attach a thermal reservoir with the same temperature. Throughout the process and make it in a thermal contact with the gas. Then it can either supply or absorb heat. We remember that delta Q equals 0 for free expansion. Delta W equals 0 for free expansion. And delta T equals 0 for free expansion. However, we would like to reproduce the free expansion effect in the gas only. So what we want to do is keep the temperature the same. We keep it. However, we allow the heat transfer from the heat reservoir to the gas. To keep it at the same temperature, supplied heat should be the same with the amount of work done by the gas during this expansion. So this is not actually a free expansion, but the gas has been supplied by this heat reservoir with the non-vanishing amount of heat. Instead, the same amount of heat is used by the gas as a work. So net effect of the temperature is the same because of this expansion. This one requires a P delta V, right? So expansion, if we cut it off, isolate this part, then we find it is very similar to the free expansion state, keeping the temperature the same and the volume has been exchanged. The difference between these process and this free expansion is that free expansion does not accept any heat, and during the expansion process, this system is not in a thermal equilibrium. Therefore, we cannot make use of this ideal gas equation throughout the expansion process. However, if I attach a heat reservoir with the same constant temperature, what we can do is we can make throughout this expansion process, we can make use of PV equals NKBT throughout this process, because at every stage the gas is in thermal equilibrium at temperature T, and pressure, both the pressure and volume, are well defined. That is not true for a free expansion. It is an isolated system, and this is a different system, different from an isolated gas system. However, if we just focus on the effect on this gas system only, then everything is the same. In addition, they are in thermal equilibrium and the points are the same, although the middle process, intermediate process, is different from of free expansion process. The difference is that we can do any calculation because all of the thermodynamic variables are well defined in this process. So we match the initial and final state with those of the free expansion process and forget about this uncalculable intermediate state, then we can do any calculation regarding the what we want. Okay. The requirement, initial and final, there is no energy difference. Temperature difference is no. Instead, the gas system does work, and that amount of work is the same as the supplied heat from the heat reservoir. So this is a reproduction of the final state using a reversible process. This is not a reversible process. It is irreversible process. That means in the middle of the process, it is not well defined. However, we modify the system into a mixed composite system with the heat reservoir. The intermediate states are well defined and we can compute anything, any difference between the two initial and final state. This is what we can do. As we have done, internal energy doesn't change. And when it accepts the heat, it does work and the amounts are the same. So the temperature is invariant. The amount of work is done, the amount of heat is transferred to the amount of work, and using PV equals NKBT, we can compute the accepted heat during this reversible process. It is also possible to evaluate the difference in any thermodynamic variable during the process of this free compression process in a similar manner. Example, the work done by the gas or the heat transferred to the gas from the heat reservoir can be computed by evaluating the integral PDV from the initial. In this case, initial is V2 and final is V1 for the compression process. For the expansion process, from V1 to V2. 9. An isothermal process at a temperature T from the initial to final. This calculation shows that PV equals NkBT, and we have the single temperature, so pressure should be NkBT initial 1 over V, and this is constant that we have factored out from the integral, and integrand is just simply 1 over V, yielding the log integral, and the final for the expansion is NV1. Therefore, we have 1 over N, and the final result is negative. Using this idea, the heat transfer from the heat reservoir to the gas is regardless of whether it is an expansion or compression. It's a VF final divided by initial log. We divide both sides by the temperature, so delta Q over T is simply NkBT log ratio of the volume. Actually, this one is called delta S. That is a change in the entropy. In an isothermal process, and in a process of expansion, isothermal and expansion, the gas accepts the heat, so the heat supplied by the heat reservoir is a positive. And the reverse, it is a compression process. It is a negative. So entropy increases when the system accepts heat. Entropy decreases when the system releases heat. Because the free expansion satisfies free expansion. Free expansion. In free expansion, actually the free expansion delta Q equals 0. In the carbon copy of the free expansion, by making use of the thermal reservoir, that reversible process has delta Q is positive. That is isothermal expansion that is positive. So we should, this 9D should be corrected. Anyway, during this process, delta Q is negative. During this process, delta Q is a positive, remember. The change delta S in entropy in a thermal system is defined by, yes, delta S is delta Q over temperature. And because T is not Celsius, not Fahrenheit, so it is absolute temperature. So it is, except for the absolute zero, it is always positive. Therefore, the sign of the entropy change is the same as the sign of the heat transfer to the gas. In a free expansion, the entropy increases because the corresponding, this is expansion, not exactly the same as the free expansion, but the copy of the free expansion by attaching the heat reservoir. In expansion, delta Q is positive. Therefore, delta Q over T is positive. That is the change of entropy. So entropy increases during the free expansion. What we have done is by making use of isothermal expansion to know the change in entropy from here to there. We have never made use of explicit free expansion process because during the expansion process we cannot compute anything. We don't know how to describe this expansion process. Instead, we make use of initial final state only, and we find the same initial and final state and replaced the intermediate undefined state with a well-defined reversible process. During this free expansion, it must accept heat because it has to work when it expands. So delta W is a positive as well, and delta Q is a positive, and delta Q and delta W are the same. So this is a isothermal expansion. By making use of isothermal expansion, we were able to compute the entropy change from the initial to final state of a free expansion process. Okay. Accordingly, a free compression process, the entropy decreases. Entropy decreases because it releases heat. The work done by the gas is negative, and if a process happens spontaneously and delta S is greater than 0, just like a free expansion, then the process is irreversible. Right. The reverse process is a free compression, and free compression has delta as a negative. In the next class, we will learn that this process does not happen spontaneously. That is called the second law of thermodynamics. Process is reversible if delta S is 0. The reverse of a process may happen spontaneously. Reversible process, delta S equals 0, so the reverse process, its reverse process also has a delta S equals 0. And actually it is closely related to the probability, and actually it is a log probability. Okay, next problem. This problem is the same as what we have done already. Mixing of cold water at temperature A and hot water at temperature B, and with the same heat capacities, then the final temperature is just arithmetic average of the two initial temperatures. Let us compute the entropy change during this process. This is an irreversible process because the probability of finding water whose temperature is separated into two pieces. The mixing up is okay, it's spontaneously happening. However, one cannot separate a hot water and cold water. We expect the entropy increases during this mixing process, and the reverse process does not happen spontaneously. That means the reverse process has the entropy change that is negative. That does not happen according to the second law of thermodynamics. Let's see. The infinitesimal change in entropy, ds, is dq over T. We have cold water and hot water, and this is the final temperature in thermal equilibrium. We have the same heat capacity. So we do not attach the subscript identifying A and B because they are the same. The heat transfer, okay, it is just a carbon copy of the free expansion process. We don't know how to compute the intermediate state from the initial to final of a free expansion. Instead, we copy the initial and final state, and we attach a heat reservoir to keep it the same temperature. In free expansion, temperature doesn't change. Therefore, what we have done is to attach a heat reservoir keeping the same temperature. Here, we mixed cold water and hot water. And after mixing up, the final temperature becomes Tx. Now, this is in the middle of mixing, the state is not in a thermal equilibrium. Some part is cold, some part is hot. But at the final stage, we have reached Tx, that is in thermal equilibrium. So during the process, there is no way to follow up because we don't know how to describe a system that is not in equilibrium. Instead, what we want to do is to attach this cold water to a heat reservoir R. This cold water is called A. RA, and vary the temperature of this one, TA to Tx. Then initially it was at TA, and at the final stage it becomes Tx. In a similar manner, we attach a heat reservoir RB that has the temperature, hot temperature TB, and vary this temperature to Tx very slowly. Then, because throughout this process, it is in thermal equilibrium. At the same time, this part is in thermal equilibrium too. The difference between this combination from the previous case is that this temperature is fixed and the temperature varies. That's the difference. All right. So according to energy conservation, cold water, final temperature, hot water reaches the final temperature. The heat transfer should be 0. The total heat transfer is from the hot to cold. The amount of heat released by hot water should be the same as the amount of heat accepted by the cold water. That's the reason why we have obtained the final temperature. Now, in our reversible replacement, by attaching a heat reservoir of a variable temperature, we can compute the change in entropy because the temperature is well defined throughout the process from the cold state to the final state. It is not a gas, so we cannot make use of PV equals NKBT. Instead, it is the heat is proportional to the heat capacity. dQ equals CdT. So we replace this dQ with C times dt, and it becomes a log integral. So it is a positive. And B, hot water cool down. It cools down. Again, we have the same heat capacity, so dQ is replaced with the CdT. Again, we have log integral. Instead, because the system released the heat, we expect that this is a negative. As we have expected, final temperature is lower than the hot initial temperature. Therefore, it is negative. Anyway, the sum of these two should be this. And if we sum, where is it? Tx is 1/2 Ta plus Tb. We have this one twice, so Tx squared appears. And factor of 2 is a square to have factor of 4 in the denominator. And this is Ta, Tb. Sum will sum of logs will produce the product of arguments. Middle school students can compute that this TA plus TB squared subtracted by 4TA TB is just factorized into TA minus TB squared. That is a positive definite, except that it becomes a zero only if the hot and cold water were at the same temperature. Because of this one is always greater than this one. That means log something and something is greater than 1, then it is positive. It becomes a 0 only if the two temperatures are the same. That means except at TA equals to TB, that is delta S equals 0, that is reversible process. If TA is not equals to TB, then delta S is a positive. Delta S is positive, and that means it is irreversible process. What we have done is the sum of entropies of two waters. However, if we consider the entropy change of the heat reservoir that is attached to A, the additional entropy change of the heat reservoir that is attached to B, because the amount of heat supplied by the heat reservoir to cold water, amount of heat that is actually absorbed by the heat reservoir from the hot water, they are identical to each other. Therefore, they cancel exactly. Therefore, the whole system, cold water, hot water, heat reservoir attached to the cold water, heat reservoir attached to hot water, sum of everything should be 0. That means the whole system, including both cold and hot water and the heat reservoirs, is making a reversible process. However, only a partial process that excludes the heat reservoir, they have the same initial and final state, is hot and cold and mixed up. If we consider only this difference of the water system only, then the entropy increases. Therefore, mixing the water, hot and cold water, is a irreversible process. Okay. 13. Entropy change in a sample of ideal gas. According to the first law of thermodynamics and the ideal gas equation PV equals NKBT, P over T equals NKB over V, right? dQ over T is nothing but the change in entropy in the infinitesimal version, and dQ can be expressed in terms of according to the first law of thermodynamics energy change, and PDV. Okay. Therefore, the ds is CV dt over T, and we have this one. P over T equals NKB over V, so NKB over V is here. Next, the entropy, why don't we divide both sides with CV? Then ds over CV equals dt over T and dV over V, and what happens to this one, CV? And I told you we have to memorize NKB is a CP minus CV. So it is a CP over CV minus 1. And I also told you you have to memorize this. This ratio is called gamma. So gamma minus 1. Using this, we can evaluate the integral. This is constant. We have change in entropy in here, and CV is multiplied to the right side. Integral of this is log of final to initial, and this one is a volume ratio of final to initial. We can make a guess that we can construct a formula for the entropy that is related to this expression. So let's try. The total differential of the equation PV equals NKBT divided by the original equation reduces to. So this is PDV VDP, right? This is NKB dt. And then divide both sides by this amount to the left, to the right. And it becomes dP over P, dV over V, and this vector cancels and dt over T. Now let us substitute this one in here. Then left-hand side is here. Right-hand side, dt over T is replaced with this one. And then we copy this term. In here, we have minus 1, and this is plus 1. So this one cancels. So there's a log integral of pressure and gamma times the volume integral log volume ratio. As a result, this one can move up. So PFPI times VF over VI with gamma and log in total. So this one is expressed in here. And then CV can goes up, then it can go up. So CV is copied in here. We expect that entropy formula can be read off from this expression. 13. So we have to remember gamma is a CP over CV. CV, it depends on the structure of a molecule, and F is the number of degrees of freedom of a single molecule. Then CV is expressed as a 1/2 NKBT multiplied by the number of degrees of freedom. And we know CP minus CV equals NKBT. and KB. So because of this, we have this. As a result, gamma can be expressed, gamma is by definition this, and Cp is expressed as a Cp Cv plus NKB, and Cv over NKB is F over 2, something like that. Because of that, we can always write like that. Moving this one to the left-hand side, gamma minus 1 is a 2 over F. And moving it to the left, we have this constraint. So we have these two relations. By making use of this and applying those relations to the value of the change in entropy, we can simplify the expression like that. Sure, entropy is just like the potential energy, only the differential or change in entropy is important. We can add any constant without changing any physics. So this expression is almighty. From this, we can read any of them. The entropy increases proportional to the number of particles. And entropy increases at a fixed temperature. At a fixed temperature, it is log V over V0. Here, at fixed temperature, it vanishes. It is just 1. So we have V over V0. We remember we have computed the entropy change in the free expansion somewhere. Where is it? Entropy change in the free expansion from the initial to final state. We have NKB log Vf over Vi. That is consistent with this, our master formula for the entropy. Entropy increases proportional to this one at constant volume. At constant volume, this one vanishes. We have F over 2 NKB log temperature ratio. N can be read off from the entropy as this. In here, how can I read off the entropy? Because V is in here, log V, partial derivative of entropy with respect to log V, and then divide this one by Boltzmann constant, you will obtain the number of particles. Cv can be read off from the entropy. Cv appears here. So log temperature. You can take the partial derivative with respect to the log temperature, then you can read off Cv. The entropy of a sample can be expressed as, that is already we have obtained in the previous problem. T0 and V0 are arbitrary constant of dimensions, temperature, and volume respectively. Okay. The entropy change is in units of Boltzmann constant. Yes, this is a pure number, dimensionless number. They are also pure number. The entropy is proportional to Kb. So unit of entropy is Kb. That's correct. Entropy change is proportional to the number of particles. Every we have number of particles. In CV, number of particles is contained in it. The entropy change is proportional to the number of degrees of freedom. CV. Where is CV? CV is here. Number of degrees of freedom is proportional to CV. So, through CV, the entropy change is proportional to the number of degrees of freedom, F. The temperature dependence is logarithmic. Temperature dependence is logarithmic. Okay. The entropy of a gas sample can be expressed as, yes, we know, at constant volume, at constant temperature, at constant temperature, this one disappears and it reduces to nkb log V over V0. The entropy change, okay. If Vf equal Vi times N, that's right. Absolute value of entropy doesn't matter. So we can, if we substitute V0, it is log 1, and that is 0. The only physical one is the difference between them. Difference is nkb log n. At constant temperature, PV equals nkb, so V is expressed in terms of 1 over P. Therefore, it is reversed. Volume divided by V0 is to be replaced with the initial pressure divided by pressure. 17. Find the false statement regarding Boltzmann's statistical definition of entropy. And Boltzmann's statistical definition of entropy is Kb log multiplicity. For example, we distribute n molecules into beans. We want to make a half of this empty. Then we have two choices. Let a single molecule on the right, either on the right or on the left. However, if you evacuate the right-hand side, then we have to fill n molecules in a single bin. The number multiplicity is just putting everything on the left side. That is just a single case. If we take the log, it is a 0. What happens in this case? We distribute 1/2 of n particles on the left beam and 1/2 of n particles on the right beam. It becomes like that. It is proportional to log 2. Then this log 2, we are familiar with this. This log 2 is nothing but the change in volume at the same temperature. We see the entropy change is proportional to log n. proportional to the ratio of volume. Ratio of volume. Volume has been increased twice. So law, the entropy is KB log 2. Entropy change from this to that one. All right.